If you've ever had to deal with, say, a really complex organizational chart, or even just navigating a massive file system on your computer,
Yeah.
start at the main drive, clicking through folders, then more folders, just to find one file, you've already kind of intuitively understood hierarchy.
You have. And that branching structure is one of the most fundamental concepts in computer science.
So today we are doing a deep dive into the world of trees.
We are. It's a hierarchical data structure that really it dictates how computers organize, search, and process just huge amounts of information efficiently.
Our sources for this lay out the essential architecture, right? Defining nodes, branches.
And they show us some specific, really high-stakes applications, the kinds of things used inside modern compilers.
And I think the big question we want you, the listener, to walk away with is this. How does moving from a simple line of data to this complex branching hierarchy solve problems that linearity just can't handle? Specifically, how do these abstract structures solve that fundamental real-world issue of ambiguity? Something like a math expression.
To really get that, we have to start by comparing a tree to its more linear cousin, the linked list.
Okay.
In a linked list, a node holds some data and then a reference to the next thing in the sequence. It's essentially just a memory trace.
It's a chronological sequence, first this, then that.
Exactly. The single biggest leap from a linear linked list to a tree is moving from just remembering the next step to modeling. Well, to modeling causality or dependency.
Ah.
In a tree structure, a node has its data, but it can have multiple references to other nodes, which we call its children. And that allowance for branching is what makes the hierarchy possible.
So, if I'm getting this right, a linked list is good for storing, I don't know, historical records in order.
Sure.
But a tree is designed for storing complex relationships, like who reports to whom in a company, or how specific bits of data depend on each other.
That is the core distinction. And because they're designed to model those relationships so efficiently, trees are used everywhere. For searching, for sorting, for massive data organization.
And the sources mention a few specialized types.
Yeah, things like binary search trees, which are all about lookup speed, or B trees. I mean, you realize that these structures are the operational core of basically every database index out there.
Wait, why go to all that effort, though? If I just want to search some data, why is this hierarchical thing better than just, going down a super long organized list?
It's all about efficiency. I mean, pure raw speed.
Okay.
If you have a list of 1,000,000 items and you want to find just one, the computer might have to check, 500,000 of them in the worst case.
Right, on average.
But a tree, specifically an organized one, lets the computer eliminate half the remaining search space with every single decision it makes.
So finding one item out of 1,000,000,000 takes
A handful of decisions, not millions.
That's a dramatic speed up. Okay, let's narrow in on the most common one we need to understand first. The binary tree. What's the fundamental rule that makes a tree binary?
The binary constraint is simple, but it's absolute. It means each node is limited to containing a reference to, at most, 2 other nodes.
At most 2.
And those 2 potential references are always labeled the left and the right subtrees. And just like any data structure, the node itself contains the actual payload, the data we care about.
I've always found the formal definition of a tree to be one of the most, elegant concepts in computer science. It feels almost philosophical.
Well, what's fascinating is the recursive definition. Trees are, by their very nature, recursive.
Right.
So the definition applies to the whole structure and any part of it. A binary tree is formally defined as either 1, the empty tree, which we just represent with the none.
I think nothing was there.
Nothing's there. Or 2, it's a single node that contains data plus 2 references that point to a left binary tree and a right binary tree.
So that recursive definition, it means it's a structure built on self-similarity, like Russian nesting dolls.
That's a great way to put it.
Every smaller doll is still a doll, and every branch of the tree is still, fundamentally, a smaller tree.
Exactly. And that means the code you write to manage the tree only has to be written once, and it can handle everything from a single node to an entire forest.
That's powerful.
So let's nail down the vocabulary you'll see everywhere. At the very top, you have the root node.
The entry point.
It is. It's the ancestor from which everything else descends.
The starting point for any operation.
Then you have the endpoints. We call those the leaf nodes. They're the nodes that have absolutely no children, no references pointing outward.
Okay.
Everything else in between is an internal node. They have at least one child, so they're part of the branching structure, but they're not the root or a final leaf.
So using a family tree analogy, The ancestor you start with is the root. The newest generation with no kids yet are the leaves.
Hmm.
And everyone in the middle who has descendants is an internal node.
That clarifies it beautifully. And we also have to define the height of the tree.
Right.
The height is just the length of the longest path you can take, measured in edges or links, from the root node all the way down to any leaf node.
And that height measurement is critical, isn't it?
It is.
Because if we build a tree where every node only has one child, it basically just becomes a long, skinny, linked list.
Mm-hmm.
The height would be huge.
And that destroys the efficiency we were just talking about.
Right. It's no better than a list.
It isn't. The whole goal of optimizing trees is often to keep the height as small as possible relative to the number of nodes. That's what keeps lookup time fast.
And that's where those other tree types come in.
That's exactly why structures like AVL trees and B trees exist. They have these internal mechanisms to automatically reorganize themselves to keep their height minimized, ensuring search times stay optimal even as you're constantly adding or deleting data.
Okay, that context makes those advanced names feel a lot less intimidating. We've got the structure, the constraints. Let's move to where this gets really interesting. The practical utility of this, the expression tree.
This really is the aha moment for a lot of people. It solves a very tangible problem that exists in almost every piece of code ever written.
And that's the problem of ambiguity in math.
Ambiguity in mathematical notation. Exactly.
Yeah. So take the simple infix expression, 1 plus 2 times 3.
Okay. $1 plus 2 times 3, 3.
If you just read it left to right, you get 9. But if you use the standard order of operations, multiplication before addition, you get 7.
And that ambiguity is a massive problem for a computer. It needs to execute things precisely.
It can't guess.
It can't. If you feed that string of symbols to a computer, it needs to first establish the definitive structure of the calculation. And this is why trees are the natural, unambiguous way to represent it. The hierarchy of the tree itself dictates the order of execution.
Okay, so let's try to build that structure for 1 plus 2 times 3. If the hierarchy dictates the order, how do we decide what sits at the top?
The rule is actually pretty simple.
Mm.
The operation that you perform last is the one that sits at the root.
The last one?
Okay. So in $1 plus 2 times 3, 3, we know we have to do the multiplication first to get 6, and then we do the addition. So the addition operator, the plus sign, has to be the root node.
Ah, okay. The plus is the last step. So that root node needs 2 children to do its job. The left child is the operand 1.
Simple enough.
But what about the right child?
The right child has to represent the entire result of the 2 times 3 calculation.
I see.
So the right child of the plus operator isn't a number, it's another operator, the multiplication sign.
And now that multiplication node becomes the root of its own little tree, a subtree.
It does.
And its children are just the operands 2 and 3.
Exactly. So the final expression tree has plus at the root with 1 on the left, and then that subtree of, with its children 2 and 3 on the right. And that structure, just by its layout, completely eliminates the ambiguity.
How so?
Well, if you try to execute the tree from the top down, you have to wait for all the children to resolve first. The plus has to wait for to finish, the resolves to 6, and only then can the plus complete the final step.
That structural elegance is really something. It means that the computer doesn't need like an external rule book that says always multiply before you add.
Right.
The structure is the rule book.
It is. And this isn't just a theoretical concept. This is high-stakes stuff. Compilers, the programs that translate the code we write into machine instructions, they use expression trees extensively.
To do what?
To parse the code, to optimize the steps, and to make absolutely sure that the logic you intended is the logic that gets executed. If that expression tree is built incorrectly, the program fails, or worse, gives you the wrong output.
And the structure is also key for translating between different forms, right? Infix, prefix, postfix.
It is.
Which brings us perfectly to the next challenge. Once you've built this beautiful, unambiguous tree, how do you actually get the data out of it in a useful order? We have to talk about traversal.
Right. Traversal is just the mechanism for visiting every single node in the tree exactly once. And there's an order to it.
And it's recursive, I'm guessing?
Since the tree itself is recursive, the natural way to traverse it is also recursively. You define a sequence that involves visiting the current node, then recursively visiting the left subtree, and then recursively visiting the right.
But unlike a linked list, where you just go one way, there are, 3 primary ways you can walk the tree?
3 common methods, yes. In order, pre-order, and post-order. And the only difference between them is when you visit the current node relative to its subtrees.
And that positioning changes the output completely.
Dramatically. Let's start with preorder traversal.
Okay, pre-order, so
Yep.
pre means before.
The rule is, visit the node first. Then, recursively visit the left subtree. And finally, recursively visit the right subtree.
So the root of any subtree always appears before its children.
Exactly. And if you perform a preorder traversal on an expression tree, the output you get is the expression in prefix notation.
Okay, let's trace our example tree. We start at the root plus a, we print that. Then we go left to 1, we print that. Then we go right to the multiplication subtree. Its root is a, so we print that. Then its children, 2 and 3.
And what do you get?
Plus 1, 2, 3, which is exactly how prefix notation is structured.
Precisely. You visit the operator before its operands. Now, let's look at in-order traversal. This one is probably the most intuitive to how we normally read.
So where does the node visit fall in the sequence here?
Right in the middle. The algorithm is visit the left subtree, then visit the node, then visit the right subtree.
Okay.
This is useful for any binary tree. But if you're traversing a binary search tree, that special kind of tree where the left child is always less than the parent and the right is always greater.
Then what happens?
An in-order traversal will output the contents of that tree in perfectly sorted numerical order.
That's a great mnemonic. In-order traversal gives you the content in order. It just extracts the sorted list.
It's its most powerful feature. Now, for the last one, post-order traversal.
I'm going to guess post-order saves the node for last.
You got it. The algorithm is visit the left subtree, then the right subtree, and finally, visit the node itself. The root always appears after all of its children have been processed.
What's the practical application for processing everything else before you get to the current node?
It has two huge uses. First, on an expression tree, a post-order traversal gives you the expression in postfix notation, the kind you see in stack-based programming.
Okay. And the second?
And this is crucial. It's the standard way you delete a tree or free up its memory.
Oh, I see.
You have to delete the children before you can delete the parent. Otherwise, you lose the reference to the children and you create a memory leak. Post-order guarantees you start at the leaves and work your way up to the root, ensuring everything is cleaned up safely.
That connects the academic idea directly to the hard reality of memory management. That's a huge takeaway.
It really is.
So to pull this all together, trees give us this elegant organizational structure. They're critical for rapid search and sorting. And as expression trees, they completely eliminate the ambiguity that can mess up linear mathematics.
That's a perfect summary.
And this structural understanding is really key to grasping how complex software and programming languages are managed and optimized by things like compilers.
Exactly. We've covered the definition, the recursive nature, the vocabulary, and the three main ways to get the data out once the tree is built.
But now for the final challenge. This brings us to the actual implementation hurdles the sources point out. We talked about parsing an infix expression like, say, 3 plus 7, 9.
Right.
We know the tree building algorithm works, but it can't operate directly on that raw string of text.
It can't. The very first critical step in this whole process is converting that raw string into a clean, structured list of tokens, the individual meaningful pieces.
So turning the visual math into a list that a computer can read, something like 3 plus 7, 3 and 3, ln, end.
That token list is what the tree building algorithm actually works with. And you notice that final element, the end token. The sources highlight that it's useful because it stops the parser from accidentally reading past the end of your input list, which would cause an error.
So here's the provocative thought for you to mull over. We've learned how to define a tree, how to traverse it, but the act of building it has this hidden first step. What steps do you have to take to reliably convert any string expression into that token list?
Think about the complexity there. You have to handle white space, multi-digit numbers, variable names. You have to make sure parentheses and operators are all recognized correctly.
And what about mistakes?
Exactly. You have to ensure that errors, like a malformed expression, maybe missing parenthesis, aren't just ignored, but are actively reported. That process, writing a function that reliably creates that token list and manages all those potential errors, that is the silent critical predecessor to every single expression tree we talked about today.
That's the real challenge that unlocks everything else.
That's where the real work begins.